Nowadays, you could see, the cell phone, the laptops, and they all require you to have high energy density batteries. And how to integrate solar and the wind into the electrical grid also needs you to develop low-cost energy storage solution in order to deploy these applications at a large scale. California has a mandate. Very soon we'll have 50% renewables in our electricity. So without storage, this is not possible. Let me say, well, where is the status of technology right now? On the black column right there, what you see is, in terms of energy density, the cost, and the cycle life of the current battery technology. The red column is where we want to be. Take the energy density as an example on the top row, and 250 watt per kilo. We want to go to 500 watt per kilo. If you could do that, a car will be able to drive 500 miles and the reasonable size of the battery pack, and the cost will be reduced tremendously with high energy density. So, and then take another parameter such as cycle life. If you can have 10,000 cycles instead of one, having a 25 years, 30 years lifetime of battery instead of 7, this could make a huge impact in terms of economy. So this is exactly the target we have been working on. It's the final delivery goal to the customer. However, we all the way come back to the fundamental science and technology we have to develop in university. So in order to increase energy density, for example, this is the graphite crystal structure. Once lithium ion going in, that's the right-hand side, that those blue dots are lithium ion. But we are seeing the limit right now. If you could invent new materials such as silicon to replace graphite carbon and metallic lithium to replace graphite carbon, you have 10 times higher storage capacity that can allow you to start to make 400 watt per kilogram of batteries, even 500 watt per kilo. So the impact can be very big. But coming back to the very fundamental material science, it's what are the problems right there? Oh, similar case for the cathode. If you can move away from traditional lithium metal oxide and use something like sulfur, much cheaper, the amount of charge storage capacity is about 1700 milliamp hour per gram, also about 10 times of the current technology. You could really enable very low cost, very high energy batteries. So, as I said, this all the way can come back to, how do you make these new materials to work if you can do that? From now, 250 watt per kilo, and then eventually we have a choice of 400, 500, up to 600 and more. The cost will be much lower. Imagine if a car can drive for 500 miles, 600 miles. I mean, that's really it. This is much more than a gasoline car. So now it comes back to the fundamental materials, and I will encourage the young people, at the same time thinking about business opportunity, but do develop your technology sense. This is the first technology I worked on since I joined the Stanford faculty, is how do we enable silicon instead of graphite carbon. Silicon is seeing this problem of volume expansion and breaking. At the time, nobody knew how to solve. As a person never working on battery before 14 years ago, so jumping into the field and started to develop the idea. The first indeed technology invented turned out to be one of the best. We published about a decade ago. It's using silicon nanostructures such as silicon nanowires to overcome the volume expansion problem. So from this in situ, this is a transmission electron microscopy, right? This is a very high resolution you are seeing right now, 200 nanometer scale bar right there. Inside the electron microscope, we could see a silicon. Once lithium coming in, the volume expansion is taking place. And it does not break for the nanowire case. But the coating, the black color is the copper coating on the surface, is really broken. This is really telling you how challenging that is in order to make silicon to work. I want to show you another in situ video. This is the case. In the center is a silicon nanoparticles, 800 nanometer in diameters. Once lithium coming in, this silicon is expanding a lot. This is in transmission electron microscope. The magnification is so big, and then any vibration you will be able to see inside the electron microscope. Now, once the silicon particle start to take in a lot of lithium, it will start to be broken. You see that causes the battery failure. Using a research like this, we can identify how small size of silicon really needed in order to avoid the breaking problem. This turned out to be, this conclusion of our study has been guiding the whole industry moving forward. You look at all the battery companies right now working on silicon, they read our papers and really try to come up with the size of silicon particles to use. This provides a lot of guidelines right there. So over the years, we started from making these nanostructured silicon to overcome the breaking problem. Until nowadays, it's been more than a decade. I won't go into the details. We have been through our 12th generation of design. So until nowadays, it's really tough. As a Chinese, many of you sitting right there, I always want my number to be either 3, either 6, either 8, or either 9, either 12. I won't end it at generation 13. I will end it right here, generation 12. I think we solved all the problems of related to silicon. Some of you know I founded a company, Amprius, about 11 years ago. And Amprius has been doing very well. Let me point out a few really, I think, remarkable achievement right there. One is Amprius silicon nanowire batteries right there, making this very high energy density of battery, 435 watt per kilogram. 1200 watt hour per liter is about 80% higher than the battery you use in your phone right there. So we have been powering the Airbus commercial drone, continuous flying for 25 days. So during the day, the battery will be charged by the solar cells, but the solar cell only charged probably for about 6 hours and most 8 hours. The rest of the time, we'll need to rely on the batteries to power. It requires very, very high energy density. So far, Amprius can supply this. And so this is really going quite well. And then the next big thing after this is how do you enable grid-scale energy storage? We didn't have solution yet, the whole society. But this market is coming up to be about $1 trillion market very soon, in about 20 years. You can see that coming. From now on to 20 years later, it's going to be $1 trillion market. So we have been inventing new type of technology, our manganese nickel hydrogen gas. These allow us to build this battery cell using very low cost materials, and the cycle life lasts more than 10,000 cycles. That's really, really long. This is the technology can go for 30 years. And nowadays, you don't see any batteries can go for 30 years. Lithium-ion is about 10 years, 7 to 10 years also. So lead-acid is about 5 years. Here is the battery you can expect for 30 years, perfect for grid-scale storage. The cost is going to be much, much lower. Over the cycle life of these batteries, per kilowatt-hour electricity storage, you could go to a few cents per kilowatt-hour. So this is the technology I see having a great potential to really break into the market of grid-scale storage and make an impact. The second example I want to share with you is PM 2.5. So for a number of years when I visited China and other countries, I see the air pollution problem. Many of you here sitting right here understand this problem. About 5 years ago, we started to really look into these areas. First of all is to purchase the facial mask on the market available in Beijing and come back to Stanford to measure the filtration effect. Turned out to be most of the facial masks do not work right there. And so we have invented a new technology. We also look into industry filtration. That's where the PM 2.5 comes from. It's either the exhaust from the power plant, from the factory, or from the car, from day-to-day driving. And there's no technology doing the exhaust filtration for PM 2.5. So we invented technology back in 2015. is to develop these polymer nanofibers. They can trap these PM2.5 particles effectively, at the same time maintaining very low air resistance, so airflow is good. At the same time, they're transparent to the optical light. So a technology like this, we actually did all the study, can filter out not only 2.5 micron, 10 micron, all the way go down to 0.3 micron. So it also can filter out bacteria and viruses with high efficiency. So a technology like this really allows us, I'm going to skip this slide, to do something like this, is the exhaust filtration. And in a car, even though when you're driving, you don't really see smoke coming out because the particle size really coming out, they're very small. They're 0.3 to 0.5 micron also. But yes, they're still very deadly. You need to remove those. And even though in California, right, if you're driving the car, you think the air quality is good, but close to the car, it's actually not. So we need to do air filtration for the exhaust. So with this research, this is Steve Chu and myself, we co-invented this technology. So a few years ago, we co-founded a company called 4C Air. We want to push this out to the market fast in order to benefit the general public. And last year in California, we noticed a fire. There's a lot of smoke coming out, and roughly in November last year. Unfortunately, our production line wasn't ready at that time to generate the solution for the general public. I hope this year, I hope the fire won't happen again. But if it does, we are ready, to ship out these products to the general public. So you can use that for your window screen. Maybe I'll skip this, right? I'll skip this. Can use that for window screen, for facial mask, and for other air filtration products. So in the last, I want to share with you that another example of technology innovation is textile. So textile has been around for thousands of years. People wear clothing, and nowadays, so what's the motivation to do innovation in textile? It comes back to, first of all, is the energy saving. And every day we spend so much energy in air conditioning. In the summertime, we cool down the building. In the winter time, we heat it up. So the set point of air conditioning is about 22 degrees Celsius. And the Department of Energy, there is a study indicating if in the summertime, your air conditioning allowed to go up a few degrees Celsius. For example, in San Francisco, you look at 28 degrees Celsius set point. We can save 45% of the energy. In the winter time, can go down to 18. We save 35% of the energy used in building energy consumption. So on average around the world, every degree C of set point change, we save 10%. 2 degrees Celsius, we save 20%. And 3 degrees Celsius, we save 30%. So that's a lot of saving. This really calls for the technology innovation. Instead of cooling and heating the whole building, can you cool and heat individually? Because the building is this table, the floor, the seats you are sitting, that really eating up all this air conditioning power. What you really need is individual air conditioning. So we have been studying this, how people dissipate the heat. So every person, individual, consume the power equivalent to 100 watts of light bulb. We are giving up all this heat. So there's a curve right there labeled as radiation. Below the room temperature, below 30 degrees Celsius at room temperature, and human body dissipates the heat by infrared radiation. So that's what you want to control in the indoor environment. So we have been able to do in the summer, in the winter time, to keep body warm. How do you get infrared radiation inside? So in our textile, we have this nanoporous metallic structure, allow air to go in and out, having the breathability, at the same time to keep the infrared radiation to yourself. We figured out the physics behind this whole infrared control. Now doing the best job of keeping your body warm. For example, if you're looking at all this data right here, this is our data in the middle. Compare with all others. No matter what's the clothing available you get from a commercial market. In order to keep your body warm, what's the lowest temperature, environmental temperature you can go down to? Our textile having the lowest temperature, so that means it has the highest warming effect. So we use this textile and produce the left-hand side. That's a vest people wear. If you take infrared camera, this is my student, by the way, and you see this person's body is cold because all the heat was trapped inside the body, doesn't come out. It has the best warming effect on the left-hand side. The right-hand side is the traditional textile. You can see the body is the red color, it's actually very hot. You are really leaking out a lot of heat right there. So we have the best warming textile so far. What about for cooling? For cooling, it's so much harder to do, but we discovered there's a couple of polymer materials, such as polyethylene, on the right-hand side that's used in your kitchen as a kitchen wrap. That's very, very low cost. So they are transparent to the infrared radiation coming from the human body, can have the cooling effect. However, they are not wearable yet because they are still transparent to the visible light. So wearing this textile will just means your body will not be colored. So we engineered a nanopolar structure in there. Now the whole thing becomes white color. Now it becomes wearable. And we also prove using this textile right there is transparent to the infrared. This infrared transmittance is 90%. But the visible wavelength, the red color right there, is become opaque. So now it becomes wearable, and this really cool down the human body. Wearing our nano P textile right here, your skin temperature almost like naked. So really cooling down the body by a lot. This allows us to save 30% of electricity using air conditioning. So we have been making this into the fibers like traditional textile industry, the porous fiber, and generating this 2-meter long clothing. This is a really coolest clothes, textile available, ever invented right there. It's really cool. So, and with all this invention, we also move forward. Can we invent a clothing? If you feel warm, you want to cool down, you wear this way. If you feel hot, you want to cool down, you feel cool, you want to warm up, you wear inside out. So we have this bifunctional textile. And in California, this is perfect. During the day, it's hot. During the evening, it's cool. So you have one clothing by wearing inside out. You can feel comfortable as if you are carrying air conditioning with you. We also invented a textile. How do we do cooling under the sun? Under the sun, there's a lot of solar energy dumping onto you. You feel hot during summer. So we have to scatter this solar energy. At the same time, allow radiation to go out. We actually have an idea. We make it successful. And this is working quite well right now. So with all this technology, so I'm trying to show you with this story, we come from the society and market need. And come back to university to do invention, developing my graduate student and postdoc. Once it's become ready, we do commercialization of this technology and really work step by step. And last, let me try to show you a new business model. I want to commercialize all this technology. I founded Amprius about 11 years ago. About 4 years ago, I founded 4CL. And then this keep having more and more technology coming. As a university professor, I'm thinking, if I do this one by one, it takes too long. So why don't I just put all the technology into our technology incubators? That's innovate technology. We have licensed about close to 20 patents from Stanford all at once, also continuously having this master agreement. They will use this technology incubator and spin out company 1, 2, 3, 4. So the first phase, by the end of the year, beginning of next year, we will be having 3 companies spin out, working on water filtration. I didn't tell you about water yet. And also the clothing, the energy storage. We'll have the soil cleanup, and we'll have a number of others coming. I hope this new type of business model can serve as a very nice platform. And we all know materials, hardware technology is so much harder than the software. The time scale and the type of investment needed it's a lot more. So we need to have a really capital-saving business model to commercialize this technology. I hope this one will be very powerful in the future. I already started to see some of the effects after raising Series A last year, and multiple technologies now are moving really fast inside these technology incubators. Now let me end my talk by thanking all of you for your attention and our organizers for the invitation. Thank you very much.